Okay, back again with another torque practice problem here. What we have in this one, this is the second problem, part A on our sheet. We have a man here, and he's kind of holding on to a beam, and there's a pivot of the beam down here. So he's kind of lifting this off the ground. In this problem, we're actually not going to worry about the man in this case, so he doesn't really exist. We don't care about him. What we're actually looking for is we would like to know how much torque is being applied to the pipe due to the pipe's own weight. So let's take a look at this one and see if we can figure that out. Now, if we think about the pipe itself, the pipe is an extended object, but it's a uniform pipe, which means we can think that all of the mass of the pipe, the entire thing, is localized in the center of the pipe. This is the center of mass, the center of gravity of the pipe, and it is acting directly down right there. That is the weight of the pipe. Weight equals mg if we remember, and we know that the pipe has a weight of 75 pounds, so we didn't even have to do any mg there. Okay. At the same time, we know going from the pivot to where the force is being applied, right there, that is our moment arm. Now, our entire pipe has a length of 12 feet, and since we're exactly in the middle of it, we're halfway, so our moment arm here is 6 feet. So for our torque equation, which if we recall is R cross F, or RF sine of theta, we right now have both a moment arm, an R value, and we have a force. That force is the weight pulling down. So we can say that this is 6 feet times 75 pounds, so there's our foot pounds, and now we just need the sine of the angle. And this is a somewhat tricky one to kind of figure out here. In the problem, we are given that this angle right here is 30 degrees. So you might feel inclined to say, hey, 30 degrees, sine of 30, boom, we're done. But that's technically not correct here. What we want to do is we want to shift, remember, this force vector back to the pivot point. So let's just redraw this. Here's our pivot over here. The moment arm is going up and to the left. There's R. And let's pull the weight vector. Let's translate it, so no rotating, all the way back to the pivot. And it's acting straight down. Well, what's the angle from R, the moment arm, to the weight? What's this large angle here? Now we immediately see that this is an obtuse angle. It's greater than 90 degrees. We just need to figure out what it is. Well, what we can do is if we look at the diagram, we know that the pipe, which the moment arm is acting on, is 30 degrees to the flat ground. And if we recall a little bit of geometry, this angle between the flat ground and the vertical should be 90 degrees. So adding the 90 and 30 up means that our angle is 120 degrees here. So we can say 6 feet, the moment arm, times the weight, the force, 75 pounds, times the sine of 120 degrees. And that will be our torque. So let's throw this in the calculator real quick. 6 times 75 times the sine of 120. We get 389.7. So let's just round that up and say that our torque here is 390 foot-pounds. Okay? If we'd like to think about what direction our torque is acting, this is a right-hand rule scenario, we can recognize that the weight of the beam is causing this beam to rotate downwards. Like if the beam were to fall, that's the way it would fall. And this way, if we think about the circle it would create, is going counterclockwise. If we take our fingers and we turn our fingers counterclockwise, we'll see our thumb pointing out of the page. So if the page is, down in front of you and you turn your fingers in the same way that that beam would be falling, your thumb will be pointing out of the page there, and that is the direction of our torque. We can think about this torque as being out of the page, counterclockwise, and counterclockwise in mathematics is also thought as the positive direction. So those are all the directions of the torque. So right there, a little bit of center of mass, a little bit of torque principles. We ignored the man in this scenario because we just wanted to see what the beam was doing to itself. Did some right-hand rule at the end, and that's it. Quick little torque problem. Hope that helped you out. With that, this problem is finished. Go practice some of the other ones. Try part B, where we actually look at the worker's lifting force and see what kind of torque he's applying. Take it easy.